Assalamualaikum warahmatullahi wabarakatuh. Hello guys, welcome back to my channel. Now today I'm gonna show you how to simulate the finite element analysis of static structural, exactly the force or the load on I-beam. And we have a case right here that there is a carbon steel bar which is supported in two sides, point A and point B. One side is fixed support and the other side is dynamic support, which is flexible in position, and it has rollers in the bottom, and the directions that it can be moved exactly in the x-axis right here. And it is also applied by a force of 3.5 kilonewton or 3,500 newtons, and it has the dimension of this cross-sectional area for 40 millimeters multiplied by 40 millimeters, and with the length of 1,500 millimeters. Material is carbon steel with the Young modulus known for 210,000 MPa. Now we're going to determine the directional deformation, equivalent stress, normal stress, and how to create the report for the simulation in Ansys. Okay, let's get started. We open the workbench first, and don't forget to always save the file in your destination folder, whatever you like. In case that in the middle of the simulation there is some errors, you don't have to start over again. Okay, just save the file and with any name you want. Now in the toolbox right here on the left side of the window, as you can see, there are so many simulators. So I'm gonna choose the static structural right here. Just drag in the green zone, in the green box in project schematic, release it to create standalone system. And then in the engineering data, I'm gonna edit it according to the case that we have before. In the properties of outline row, in the engineering data tab, exactly in the row number 8 Young's modulus. So we will change it in the megapascal, and we will change the value, double click on it for 210,000. Okay, and the others, just like a Parsons ratio, bulk modulus, shear modulus, and the others, I just want to keep it. Alright, we switch the tab to project once more, and we go into point number 3, geometry. Make sure that the analysis type row number 17 in the properties of the schematic is already in 3D. Just let it be in 3D, and then we gonna open the design modular geometry. Just wait for a few seconds until the window is open. Okay, now in here in the tree outline, we have 3 planes right here. Now I'm gonna use the XY plane. Right click on it, look at, and don't forget to change the units. That is in the default, it is in meter. I'm gonna change it in millimeter. Okay, now we switch the tab from modeling to sketching, and don't forget to turn on the grids, show in 2D, check it, and also check the snap box. So now we already have the grids right here. The big boxes represents one big box represents 10 millimeters, and one big box consists of five small boxes. That one meaning that one box similar or represents 2.5 or 2.5 millimeters. Okay, now I'm gonna draw a rectangle right here according to the case. It is 40 millimeters multiplied by 40 millimeters, meaning that we have to draw in the 4 boxes multiplied by 4 boxes. Okay, to make sure that our dimensions is correct, we just click dimensions, let it be in general, click the horizontal line and also the vertical line. In the details view, bottom right corner right there, we can see that it is already 40 multiplied by 40. Now it's correct. Now we switch the tab modeling once more. We expand the XY plane, activate the sketch 1, and then click extrude in the task pane up there. In the details view geometry, click apply for sketch 1 that has been selected, and then in the depth we're gonna apply it for 1500 millimeters according to the case, and then click generate. Now it's already turned gray, meaning that our 3D model has been successfully created. If you want to see it, perhaps you just want to look at it and rotate it, freely rotate it. Okay, this is our model. Alright, now we go back to the workbench window. We choose point number 4 model, right click on it, click edit. Just wait for a few seconds until the window is open. Okay, this is our model window, our meshing window. Okay, now what we're gonna do first is we're gonna set the mesh. Just simply click the mesh in the tree outline of project right there. Look at the details of the mesh in the bottom left corner. In the element size, which is in the default, it will be in 0. We'll change it into 20. Don't forget to change the units from meter to millimeters. Once more, I change the element size into 20, and then we generate the mesh. Okay, the mesh has been done. Seems to be very good. And then we will apply the fixed support, dynamic support, and also the force. Just right click on the static structural in tree outline, and then click fixed support. For details of fixed support in the geometry, they will ask us which one of the geometry we will use. We just activate the edge selector right there, and then click this edge. Probably want to zoom in. Okay, click apply. Now we have our fixed support right there, and now next I'm gonna apply the displacement right here. There's that. Okay. Okay. All right. Just the opposite position from the fixed support. Okay. Now we right click again, click insert displacement, and now in the taskbar once more we click the edge selector. We click this edge, just exactly opposite with the first of the fixed support edge. Click apply, and then I'm gonna set the X component into constant, because we already know that our support is laid down on the ground, and it has a rollers above below it, and can only freely to move in the Z component or Z axis. So I'm gonna put the X component and Y component in constant. Okay, now the next thing is to do that we will apply the force. Okay, in the edge select in the taskbar we click the face selector, we activate it, and then in the geometry we just select the above face of the model and then click apply. For the magnitude we will enter into 3500 newtons, and if you see the arrow is pointing upward. Now I'm gonna change it, just click the direction, click to change it into downward. Now the second or the bigger arrow has been pointing downward, and then click apply. Right, we have done applying forces, and don't forget to change the applied by from surface effect into direct. Okay, next I'm gonna insert the solution for directional deformation, also the stress for equivalent stress. Okay, and I'm gonna put the convergence plot right here, convergence plot. Okay, and I'm gonna input allowable change for 1%, which means that we will plot the convergence for a couple of runs right here, and between first run into the second run and the others, the allowable change from the first run into the second run is only 1%. So the point is that the purpose of the case convergence, because I want to make my simulation or my solving of the solution is much more accurate. Okay, and then in the solution we define for the maximum refinement loops for the mesh, for adaptive mesh refinement, for three loops. Okay, then right click in the solution, click solve. Now we're gonna wait for a few seconds right there. We can also click the progress right there in the bottom left corner to see what happened. Okay, it's ready, it's done. Now we can check the directional deformation. As we can see in here, this is the directional deformation of our model, and this is for the equivalent stress. Okay, in the directional deformation, actually we can also display the results for the counter in the smooth counter, also in the counter bands or in the iso lines. Now I'm gonna plot it in the smooth counters. We can also turn off the the elements. Just click no wireframes or show it under form wireframe. Okay, I'm gonna show the elements or the mesh right there. Okay, now as we can see here that in the legend, the minimum value of the directional deformation represented by the blue color, the maximum value represented by the red color, it is on 0.0015 for the millimeters for the maximum, and minus 0.002 millimeters for the minimum directional deformation. Okay, for the equivalent stress, it is 61 megapascal right there, 61 megapascal for the maximum, and exactly at the middle of our model right there. And the minimum, both are on the support, either this fixed support or the dynamic or flexible support. Okay, we can also create section plane right here. I'm going to teach you how to create a section plane. Just okay, in the bottom left corner right there, we just click the section plane, or probably we want to create in the home. There is a section plane button right there. Just click it, simply click it, and then we create a line anywhere we want. Just want to show the section plane in the middle, so I want to create a line right here. Okay, right, or probably I want to create the section plane exactly perpendicular with the model. So I just deactivate it first. Okay, and then okay, in this view I think it will be much easier. Just got the section plane right here. Okay, all right, we rotate it. Okay, we can zoom in. Okay, so we can see in here that in the middle of the model, the color is almost all blue or light blue or green, which means that in the middle the equivalent stress is in the lower value, maximum is on the outside of the model. So we can also find out the values for each section. And how to do that? First we click the maximum and we click the minimum. Now we already know that the maximum point of the equivalent stress is in this position and the minimum is in this position. You can also probe that to see each point in the picture, each point in the model, how much the results, how many for the results of the equivalent stress right there. It's very easy. We can also click it to simply mark on it. You can also discover the locations of the values right there. Okay. And probably we want to discover the others. Okay, if we want to delete it, just simply click label right there, just click this, hit delete in your keyboard, okay. All right, now I'm gonna deactivate my section plane right there, and the next things to do, I want to probably I want to see the chart or the graph plot for the directional deformation and the equivalent stress. First things to do, I want to create a path right there. Just simply right click on the model and then select the construction geometry, click path. Alright, for the position of the path, first we click this H, activate the H selector right there, click this H, first H, okay, click apply, and the end of the path we click the location, click the change. We're gonna click this path, the other end, reverse to the first H, click apply. Now we have already created our path right there. Okay, now I'm going to show you how to plot the graph for the directional deformation. Right click the directional deformation first and then duplicate without results. Okay, now in the scooping method we change it into path, and in the path we choose path that we have already created before, and then we right click on the directional deformation to evaluate all results. Okay, if you want to see this, probably you want to see this, there is a graph right there. Okay, all right. Okay, this is the plot for the directional deformations right here. Start from this point, from the start point, there is a minus 4.8 millimeters right there, and then it will be going down in the middle, exactly in minus 3 and minus 0.0003 millimeters right there. Okay, sorry, it is 0.00048 millimeters, and it will going down to the middle, and then it will going up again. All right, the next I'm gonna do a plot for equivalent stress. Just right click on it, duplicate without results, expand it first, delete the convergence. I don't need the convergence right here, click delete. Yes. Okay, now in the scooping method we choose the path, and the path which is path that we have already created before, right click on it, evaluate all results. Okay, now we have the plot of our equivalent stress plot for the graph right here. Since the law was value of 0.34107 megapascal, and it will go up until the middle. For the maximum is 61.503 megapascal. Okay. Probably I want to plot also the normal stress right here. Okay, evaluate all results. Okay, in the orientation we choose the z-axis. Again, evaluate all results. All right, as we can see in here, there is a difference between the equivalent stress with the normal stress. In the equivalent stress, as we can see, the maximum value indicated by the red colors happened in this both of the surface area of the top surface and also the bottom surface, but in the normal stress it's different. In the top surface it is blue, indicates by it's minus 61.539. so actually the it represented by the blue color because it wants to show that there is a pressure from the top and also the tension in the bottom, so which means that it follows the directions of the force or the directions of the load, so which means that the bottom surface of the model, which is in line with the direction of the force, is represented by the positive value, and the top surface, which is reverse with the direction of the force, represented by the minus value. So this is the normal stress going to be. Okay, the next things to do that probably I want to plot the other graphs for equivalent stress, but the position is on the middle of the model. So the first things to do that I'm gonna duplicate the already created file, already created path, so just duplicate it, and in the details of the path number 2, second path, okay, we just put the y coordinate from 20 millimeters into 0, so it's gonna be slide a little bit in the middle, and also at the end point we change the y coordinate into 0, hit enter. Okay, it's done. Now our path has a little bit slide into the middle for a second path. Now I'm going to duplicate the equivalent stress, duplicate without results, once more to later convergence. Okay, and in the scoping method, in the details of equivalent stress number 3, we change the geometry selection into path, and the path we select path number 2, right click in the equivalent stress number 3, and then evaluate all results. Okay, if we see the graphs right here, it's a little bit different with the previous our top surface position, just a little bit different right there. That in the top surface of the model, the graph is reversed with the position of the middle graph in the middle, that the color of the equivalent stress in the middle is totally blue, which indicates that in there is a lowest value of the equivalent stress, and there is a little bit tension in the axis, or sorry, in the support right there. So that's why the color in there is represented by a red color. So there is a little bit different in the finite element analysis, that the top surface will be colored in red, and the value of the equivalent stress right there is the highest, because it contacts directly with the force right there. So there is a little bit tension in the surface and also in the bottom surface, top surface and bottom surface, rather than in the middle position of the model. Okay, the next thing is to do that I want to plot the charts for the entire charts that we have created before. In the results, just simply click home, and then in the task pane we select chart right there. Okay, and the next I want to also plot the boundary conditions in the static structure, and just click images, click figure, just zoom out a little bit. Okay, and then I want to also create a figure for the directional deformations. Click image, figures, zoom out a little bit, and also I want to plot for the equivalent stress figure, zoom out a little bit. Okay, and also for the normal stress. Okay, we have done it. Now just simply click report preview. Okay, wait for a few seconds that Ansys will generate the report for us. Okay, I think there is some of cut picture right there in the geometry. Okay, I think I will change it a little bit. Just go back, close the report preview, click the construction geometry. I will zoom out it a little bit. Also in the boundary conditions, I think everything is alright. Click the report preview once more and wait for the Ansys to generate the report. As we can see in here that the preview is quite complete, since the information of the geometry and also the information of the mesh, and also the mesh, and also the information about the analysis. This is the boundary conditions, convergence plot, and also the figure for directional deformation, equivalent stress, and also the plot for the equivalent stress, the directional deformation, and also for the plot of equivalent stress graph in the top surface, and also the equivalent stress in the middle position. So it's very, very complete that probably you want to print it out as official result of the simulations. Okay, that's all that I can show you how to do the simulation for the I-beam static structural analysis. Don't forget to like my video, and probably you want to comment in the comment section, and probably you want to subscribe my channel. I will say thank you very much for that. Okay, that's all I want to show you. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.